Okay, so hello everyone. It's a pleasure to be here and to have the opportunity to show some of my work that I did in the last years with you as such a fantastic audience. My name is Stefan Raith and I'm working at the Aachen University Hospital. This is a factory-like building here, which is actually a hospital. And my talk today is called Blender as a Swiss Army knife for medical research, because it's so versatile and it has so many different areas of application. For me, it really resembles a Swiss Army knife in my daily work. So I'd like to first introduce myself a little. From my education, I'm a mechanical engineer, studied at Technical University of Munich, and afterwards I specialized on application of computer science in medical fields like plastic surgery, face surgery, and also dentistry. And I was working at the University Hospital of Munich first, and afterwards, and I'm still today working in Aachen. And my question to the audience would be, is anyone else dealing with medical tasks in his daily work? Yeah, there's a few, so happy that I'm not the only one to use such an exceptional task. So going to the next, my personal path, how I started with Blender. And in the very beginning, during my studies, I knew that Blender was around, but I pretty much felt like in this cartoon where someone would offer me wheels, and I would say like, no, I'm too busy, I have deadlines to meet, and I can't really afford the time to go into really getting to know this new software. Even when I opened Blender at that time, I was just overwhelmed by the many buttons, and I didn't really have a clue how to get into it. And then something happened, and that was I played soccer and I ripped my Achilles tendon, and then I had basically to put up my foot for a few weeks and couldn't work. And this is what my days looked like during that time. I watched basically Blender tutorials, keeping my foot up, and some like from Andrew Price or Zacharias Reinhardt that I saw floating around here at the conference as well. So that really gave me the first introduction to Blender, and that helped me first to visualize things that I did in my daily work, like here really clumsy visualization from 2011 where I tried to visualize our mechanical testing device for human bones and also bone substitutes. And another one from plastic surgery where I tried to visualize the principle of laser barrier 3D scanning of full body shapes. And that was fair enough for presenting principles. But then I realized that Blender has so much more to offer with its capabilities of scripting. And today it's really the major link in my interdisciplinary research that I conduct between me as an IT guy or an engineer and my medical colleagues. And that's because it has a really customizable graphical user interface that really allows us to connect the algorithms that I'm programming with the medical doctors that have not a clue on what's happening under the hood. And also the availability of scientific Python packages for more complex programming is a huge issue, and then the easy distributability, like we can easily install Blender on computers of students or PhD candidates and don't have to deal with license issues at all. So here's an outline of my talk that I will give today. I always will start with the medical questions that my surgical or dentist colleagues have, and that is symbolized by the question mark and the head of the medical expert. And then I will go into detail on how we implemented solutions in Blender to help solve these questions, and then basically turning question marks in the head of the medical experts into light bulbs, though they have the idea what's going on. And then finally, I would highlight the presentations that we do in the publications that we do in the end, because as researchers, we always strive for publications to contribute to science in general. So my parts that I will show today are from biomechanical simulations in facial surgery, also plastic surgery, and topology optimization example, and also statistics and modeling is one essential topic where we deal with anatomical data a lot. Then measurements in 3D spaces, of course, one really great application for Blender in this use case, also a 3D comparison, then designing of parts that can be 3D printed, and also artificial intelligence application in dentistry I would like to show. So my first clinical question that is a rather general one, that would be how to extract anatomical features from 3D data. So my medical colleagues often work with data like surface scans, MRI or CT data, and are interested in distances or relative angles and so on. And for that application, Blender is really a useful tool. We can easily program specific add-ons that conduct several measurements. We can create workflows and apply graphical user interfaces that can make these measurements and export the data in text or Excel files. And what we also can do is we can automatically detect several measurements, and that is important when we want to batch process large numbers of 3D data sets. Like in this example that I show here, we had a task where we should extract the measurements on mandible bone, so that's lower jawbone, and our task was we have almost 500 scans, and we automated the whole procedure of detecting these landmarks that are shown on the lower right side automatically in a batch process running completely in Blender, and then we could make the statistical evaluations out of it, create a mean shape that is valuable for biomechanical experiments, that you don't just simulate one random geometry, but real mean geometry out of a large collective. And here's statistical data that we extracted, quite a lot, of course. And believe it or not, even these bar charts here were created in Blender. That shows how versatile the software actually is. We just created a Python script that adjusts bar heights according to the statistical data, and also puts in the correct labeling on the axis. So that may be a rather over-the-top use of Blender, but it really shows what is possible. Next, a rather generic example would be the comparison between 3D surfaces. That is always an issue in our daily work. In examples like dental scans or full body scans and also facial scans, we are concerned about accuracy, asymmetry, and comparison between pre- and post-operative situations. And here we developed a workflow in Blender that is used as an add-on, which allows first a best fit alignment, which with iterative closest points, so you can orient different surfaces in space according to each other in a best fit way, and then display its three-dimensional deviations. And under the hood, this works actually with the shrink wrap modifier that is executed several times iteratively to find the best projection, and then also the 3D correspondence, and we defined a graphical user interface to really makes this available for the non-programming experts. And like this, we could evaluate and visualize with color scale plots the deviations, for example, in dental scans, and also in body scans, where we compare simulation results with validation data on surface scans here. Another more explicit application, or a more concrete question, would be the question how to reconstruct bone after tumor removal. So imagine the part that is displayed here in red would be a bone tumor that needs to be removed, and then a gap remains, and this should be reconstructed with surgical techniques, but the surgeons really don't have a clue how the shape should look like that needs to be reconstructed if the bone in the prior state is deformed through this tumor. And the solutions that we have is we have a relatively large collective of mandible bones, and that can be used to generate a database that allows us to virtually reconstruct the shape of the mandible. And for this procedure, we use a complex mass called random field models. I don't want to go into detail on that. An external software is used to calculate the complex parts of it, called statistic on structures. And we basically regard our different anatomical shapes as differently shaped input variable of this mathematical model here. And now question arises, and that is how to define corresponding meshes, because the meshes that come from CT data are completely arbitrary meshed with triangles, and this is not very convenient for this kind of mathematical analysis that we want to perform. We need a similar topology to do that. And for this, we made advantage of the possibility to retopology basically the triangular shapes like it is visualized here. We defined a standardized geometry consisting only of quartz, and that allows us to have one standard reference. But then the question, of course, occurs, how can we adapt and individualize this standard geometry towards the individual shape that we have from the CT data? And for this particular case, we implemented a two-step procedure. First, a coarse alignment, and then an iterative refinement to capture the fine detail. And this is done first by a mesh morphing process with a Laplacian surface editing, where we define some master nodes, we call them. These are the landmarks that were automatically detected in the first example that I showed you today. And this allows deformation of the standard mesh close to the actual shape of the segmented CT data. And in the second procedure, we do basically a projection and a cascade of different modifiers, like a normal displacement, shrink wrap modifiers, subdivision surface to capture more and more fine detail, and then in the end a smoothing. And that allows us to capture with standardized meshes the individual geometry. So on the top, you always see the segmentation from CT data, and on the bottom you see the standardized geometry, and we take advantage of the 3D comparison functionality that shows us that we have a deviation that is way above 1 millimeter and most of the location. And this can then be fed to our analysis tool, where we can analysis the mean shape and also calculate some different shapes, like with principal component analysis. You can easily guess that in Blender we use shape keys to animate and to morph this kind of model, and we also can superpose, of course, different shapes to create individual geometries that really rely on the statistical data that we fed in. And like this, we can now individualize the shapes to different individual scans or CT data, like it is shown here, where the factors automatically adjust according to the given mandibular shape. And this can also be performed when only parts of our bone are known for the software. So in these examples here, we have missing parts in the middle of the jaw of different scale, and the software is capable of estimating the missing parts, and that is a very helpful information for the surgeons that need to perform a reconstruction surgery in order to plan the operation optimally, to really know how the missing parts should shape like to get the best reconstruction. So another topic that I would like to address is one coming from dentistry. So dentistry today becomes more and more digitalized. work where 3D surface scans of the present teeth are taken, and they are used to plan restorations like different crowns or dental bridges. And in this digital workflow, there's one manual part, and that is to select different teeth in the 3D scan. And our aim was to automate this detection of teeth and also the classification. So like the software should tell us is it a molar or an incisal tooth. And for this procedure, we indeed used Blender again for the generation of two-dimensional images out of this three-dimensional data that I show you here. And this is done by basically rendering and using the C-depth channel of our renders in order to create a grayscale image that resembles the depth from the occlusal plane. And like this, we can use image filters to detect the cusps. That would be the parts or the tips of the teeth. And then we create fraction of these images that are centered around the tips. And that would be actually the data that would be fit in our artificial intelligence tool. So we use a Python interface as well for this task called PyBrain. And that, of course, blends in well with the Python scripting interface of Blender itself. And we also used different fields of view to investigate which data would be the best to train and to learn this model on how teeth look like, and later on to enable it to classify teeth. So what we found is then that even with low resolution scan, though here we have only 10 by 10 pixel images, the software was capable of detecting most of these examples quite right. So the question would always be which tooth or which cusp is in the middle of these images, and it worked fairly well in most of the cases. It took the right decision, and if it was wrong, it was only always wrong one tooth cusp away, though it never occurred that it was completely off. And especially interesting was even at the low field of view scan that I displayed here, the software was capable of detecting what this is, whereas a normal human being watching these slides or these images, he couldn't really find out what kind of tooth cusps this would be. And in fact, we did a quite extensive study design with lots of different parameters that we could adjust in the AI to see which shows the best performance, and we could get up to 93.5% of correct classification, which is quite remarkable concerning the relatively limited set of data that we had to train our data. And without the capabilities of Blender to render a C-depth image and to do this in an automated batch process, we wouldn't have been able to create such a large database for our research. This, in the end, was published in Computers in Biology and Medicine. And another example is a more clinical application, and that is about a soccer player again. He had a facial fracture of his cheekbone. You can see on the 3D surface scan in the middle is a swelling on his right side. And what we did here was he requested a protection mask made from carbon fibers to return to the pitch as soon as possible. And the conventional way of manufacturing such a tool would be to make a plaster cast of his face. And that's, of course, very painful because he just suffered a face fracture. So our non-invasive surface scanning technique shows some advantages. And again, we could also compensate for the swelling part easily in a virtual environment. And we use Blender here to post-process the surface scan and also to create a scaffold structure beneath to save some material in this powder bed technique and to speed up the printing process, which is, of course, time-critical thing because the player needs to return to the pitch as soon as possible. And this is how the 3D printed template of his face looks like. And this is what the orthopedics technician did out of it. He formed the protection mask according to our digital planning and the 3D print. And then, luckily for us, the player suffered a facial fracture 2 years before and was treated with a conventional mask. He wasn't satisfied with it, but we had the old one, and then we could make a 3D comparison between the old one that is shown on the left and his face, and between our new digitally planned mask that is shown on the right and his face again. And it's clearly visible that our digitally planned mask here resembles better his facial structures, and then of course offers more comfort to wear for the player. And this was published in the German Journal of Sports Medicine as one case report. Another clinical application that I would like to show is the problem of a too narrow upper jaw. And this is treated with so-called expanders, and there is, distractors is the correct term, I think. And there are two different concepts at the market. One born at the alveolar bone and the other one at the palatal bone. And there is also different surgical techniques around that are used to weaken the bone and to allow some lateral widening of the bone. And to answer the question which device in combination with which surgical procedure would be the best alternative, we performed some simulations of mechanical stresses and deformities with so-called finite elements. And for this we created an interface that allows us to process our data that we already have in Blender to our finite element software. We used an approach that has a different software tools like ProPlan CMF for the segmentation of the actual 3D data from CT, then ISM CFD for the finite element meshing. ANSYS was used for the finite element simulations, and in the end Blender and its Python programming interface was used to connect all these parts and to form one convenient process chain. And for this we had to design interfaces like for reading FE post-processing data from ISM CFD in that case, where we can really read the whole finite element data and make modifications to it if we need it, or apply boundary conditions. And then we can export with a writing functionality this FE data in order to create input data for the actual finite element simulation of the mechanical loads. And in the end, we have a reading interface again that reads the database files from ANSYS in this case, and allows us to show everything that the mechanical simulation offers in Blender, like stresses, strains, or deformities, and like this we can make colored plots, of course, and all kinds of animation, and everything was what Blender has to offer for us. So this is a process chain that we offered. We use Blender first in the pre-processing step between the actual segmentation and the finite element meshing, and we also write some boundary condition part, like force and displacement boundary conditions that are defined in Blender already. And then we do the finite element simulation, which is run in batch process. So as there's no need to open the actual mechanical simulation software, it is really executed with an add-on from Blender, and then the results are loaded again in Blender and can be visualized according to the data that is produced. And if we want, we can export to, for example, Excel. So the capturing of the bone geometry is done in ProPlan CMF, as I already told, and we use Blender to pre-process this data to make it valid for actual mechanical simulations. And the load boundary conditions are also applied in Blender, as you see here with these arrows marked. And then we have the surgical cuts as visualized here. They are also introduced in Blender by Boolean operation with plates that have a defined thickness. And like this, we could design 3 different surgical alternatives combined with 2 different distractors. And that now allows us to perform the simulations to visualize the results. Here we see the stresses that occur in the bone and also see how the mechanical device that is visualized here only in Blender and the actual simulation is just represented by force boundary conditions, but we can easily add parts, of course, in Blender to the actual simulation data. And this shows pretty well how the distractor applies force in the palatal bone. And here we can, of course, animate this kind of simulation as well. And as you see, the color scale also follows this animation here. And then we can perform these simulations for all the given tasks, and this is very helpful information for the surgeons because according to this data they can decide which of the alternative would be the most suited for the given clinical task. So here you clearly see how different the stresses in the bone actually are resulting when different distraction devices are used, and this could then be evaluated and finally published to contribute to science again. So next thing that I would like to show is a clinical problem that occurs when implant plates fracture. So you don't need to be an expert to see the problem here. Here we have this lengthy plate that is fractured due to too much mechanical load, most likely associated with too much plastic deformations that need to be undertaken to individualize this particular standard plate. And our question was now, can we take advantage of computer methods to improve these kind of plates, and can we do it in a patient individual way? So to answering this question, we use a method called Topology Optimization that comes from math and is rapidly used in or frequently used in engineering. I don't want to go into details on the math that is behind, but I would like to show you a simple example. So this is a so-called design space of some beam-like structures that is loaded in the middle, and the algorithm is capable of distributing material according to the stresses and strains that occur in the material, and finally an optimal material distribution is provided that resembles like a framework-like structure, like a train bridge, for instance, and that is because the material is basically distributed according to optimal mechanical loads. And we now use this in the scope of planning of these individual implant plates, and here we have a very similar workflow, but with one exception. In the bottom, we also have the possibility to, in the pre-processing step, to define the design space individually and also the screw configuration. So the design space would be above the surface of the bone as it is visualized here. In this case, we have a bone fracture as an example, and in Blender we now have the opportunity to easily modify this design space and then to export it directly to the finite element simulation software that recognizes the shape of the design space that is also curved around the surface of the bone, so that the implant that is designed really aligns to the individual shape of the bone. And then we also offer a tool to position the screws according to the needs of the surgeons, because this is intended to be a tool that is used by surgeons, not by Blender experts. Yeah? So you can easily change the number of screws, and also their position follows the curvature of the design space, so they are always particular to the bone surface, and then we can export all this simulation data, and the actual topology optimization can be performed without exact knowledge on the simulation software, which is a very important issue if we want to implement this in a clinical scenario where the surgeon himself would make this kind of simulations. And like this, we can, of course, easily make different variants in screw positionings. And here I show you some result of topology optimization of such an implant structure. Here a close-up of how this looks like. And yeah, if we have different screw positionings, then we can easily see how our topologically optimal plates adapt to these different screw positionings. And yeah, finally, we can go a step back closer to reality and transfer the result that we get from the topology optimization into reality with some reverse engineering that we also perform in Blender to make a 3D printable model. And as we saw yesterday, metal printing with medical grade titanium is not a future thing, but it's a reality, and we can now easily recreate these computationally planned structures in reality, and like this we can plan patient individual plates. So another hands-on clinical question would be this patient case here. He suffered trauma where his eyeball is deformed backwards, and this should be corrected also in order to improve his vision. And this should be done by a transplant from this patient from his skull. Apart from the skull bone should be positioned under his eyeball to correct this deformity. And the surgical question was where on his skull should the bone part be harvested to find the optimal position. For that, we basically mirrored the healthy side, and this was our target geometry that was placed above the skull. And as you see here, we took every part, also in every rotation of his skull, and compared this geometry, the target geometry, to the local skull geometry to find an optimal position. We could find this as it is shown on the color plot on the right-hand side, and then this information was transferred to the operating room via navigated surgery. I hope you can stand these bloody images of a skull of the patient, but we really took the part that was proposed by the software in accordance with the clinical experience that the surgeon had to find the optimally suited transplant location. And here you see a preoperative and postoperative comparison where his eyeball really got in the same position like his healthy side, and also his vision improved in this case. So one last example that I would like to show you today comes from plastic surgery, where we were always concerned about the mechanical properties of skin tissue. That is very important for simulations of breast reconstructions, for instance, in plastic surgery. And here we used different imaging modalities like 3D surface scans, or also MRI data, so volumetric data, and combine these images with also a finite element simulation, as I've shown you before, to capture the best matching material properties. We developed quite a complex workflow how to validate our models, and that was especially tricky because we had to deal with hyperelastic material properties on the one hand side, and also with initial deformation of the breast due to gravity. So we had to implement an inverse gravity procedure basically to compensate for the initial deformation. And in the end, we were capable of performing some simulations of the breast in a standing position, and could compare the simulation result to the actual surface scan in order to validate it, and this allowed for us to find the best matching material properties for this particular task, and we also could in the end publish that work to find the optimum material properties. So one last slide would be the planning of facial corrections, so a more aesthetic thing. So imagine if you look like the guy on the right and you would rather look like a beautiful Suzanne in the middle. We can also plan and with this with Blender, and then pass this to the surgeons and really tell him how to conduct this kind of operation. So thank you very much for your attention on the one side, and also thank you to everyone who contributed to Blender. And I also want to thank everyone who contributed, as my medical colleagues and also my supervisors, too numerous to mention. And if you have any questions, just approach me during the conference or shoot me an email as it is visualized here. So thanks a lot.